I will be talking about ion transport, which is my passion in this field. And if we think about batteries, a solid-state chemist perspective would be to sketch it like this. So as you can see, unproportionally large electrodes versus the electrolyte. And the electrolyte is somehow just a separator, and it should allow for movement of ions from one side to the other. And we can agree that actually, of course, end phases are really relevant because they determine the thermodynamics of any electrochemical cell and thus determine the energy density. But as an electrochemist, I like rather to focus on the electrolyte. And the reason for that is that the electrolyte is actually determining all the kinetic aspects of any electrochemical cell. And that means it determines the speed of charging and discharging, the kinetic losses of OCV that are inevitable, the quality and pertinence of interfaces, and overall safety. So all the important things are actually determined by the electrolyte. And I dare to say that the electrolyte is the most important part of any electrochemical cell. But I guess this is not the audience that I have to convince in that. So if we think about battery research today, the Nobel Prize is given and we can pack our bags and start working on something else. But in principle, we have a long way to go in order to kind of push towards higher specific energy density in these kind of cells. So if we look at this full zoo of different kind of cells, you can see that there are some, like lithium sulfur and all solid-state batteries, that promise higher performance. So that is kind of the way to go in the future, I would say. And then if we think about the electrolytes that we need in order to make these new technologies possible, then, of course, we would need solid-state electrolytes. Polymers are one part of it. And if we think about slightly elevated temperature, you can see that actually polymers and hybrids are much closer to the target region than any inorganic. And this is, of course, related with also mechanical properties with these materials and kind of making the solid-state interface a little bit more easier to deal with. So in my opinion, the kind of new and old directions are, again, looking at alkali and alkaline earth metal anodes and trying to make these work. And then, of course, improve the interfaces. And then finally use those polymer and hybrid electrolytes that allow for low charge transfer resistances and good adhesion. And then this is the kind of the reason why I will be talking about these topics today. And this is what I have been doing at the Max Planck Institute for almost 11 years. So if some of you already heard parts of my talk, I hope you will not get bored today. So if we think about dry polymer electrolytes, conceptually, we are trying to improve both bulk and interfacial properties. And that means we need to have very high ionic conductivity that is at the end related with activation energy. So we need to have those as low as possible in order to have a good ionic transport. We heard a lot about transference number. We're trying to have materials that have they transport only cations, obviously, and the anions should be immobile. And in that sense, it's important to understand that the association constant that we have in our both liquid and polymer electrolytes is a very complex thing. So it's not only Coulombic interactions that actually count, it's all the other things that are in this work described here that are kind of related with the entropy of these highly concentrated electrolytes. And then finally, we need to have something that gives us a nice chemistry at the interface, but also allows for relatively high crossover current so that we don't end up with dendrites very quickly. And that is again related with the diffusion coefficient of our electrolyte. So it seems like a very complex thing that we have to do is kind of tune all of these parameters in order to have a really good electrolyte. And unfortunately, many of these parameters are correlated in a negative way. So we are trying to improve one thing, and then we are actually making another thing kind of detrimental. So what I have been trying to do for a really long time is actually try to understand of how the ions move in these kind of soft matter systems. So trying to apply a kind of a chemistry agnostic type of way of investigating this system so that we can apply it both for liquid polymer electrolytes, but also hybrids. And the idea is to actually try to understand what happens really in a battery. So in a battery, we typically have lithium-containing electrodes. which means that we could have actually a correlated movement of ions just because we have semi-blocking electrodes. What does it mean? It means that the lithium can enter on both sides, and we have actually concentration gradients of all of the species that appear in these kind of electrolytes, including the ion pairs, the ion doubles, and any other species that are there. And as I said, the association constant is complicated, and the number of species is dependent on the concentration. So the idea was to kind of try to understand how these specific types of ionic species, such as single ions, plus and minus, and ion pairs, contribute to the conductivity. So this S would be the conductivity, so to say, of ion pairs through this kind of mechanism. And how can we tackle that? Well, we have to do impedance spectroscopy with different kind of electrodes in the blocking condition where we look at this kind of anti-correlated motion. Then with semi-blocking electrodes where we can see this correlated motion too. And then finally with pulse field gradient NMR, where we can kind of get the average of all species, both for lithium and fluorine, if we work with lithium. And then if we are lucky enough and we can, from Raman or IR, actually extract the concentration of every specific species, and that is possible for some of the electrolytes, then we can actually have some equations with some unknowns, and we can simply kind of calculate it from these equations. And then we can actually access to the real transference numbers of each specific species, which is the beauty of this approach. So I would show you two examples of this approach. One is glyme electrolytes with a very specific, very bulky anion. And in that case, we actually see, as expected, that ion pairs actually dominate the transport in all salt concentrations. But what is also unexpected is that we see that in this case, the lithium is also kind of more conductive than the anion. And at the end of the day, we see that in this specific liquid electrolyte, at these relatively low concentrations, we can have actual transference numbers that are really, really high, which is related also first with the higher mobility of lithium versus the anion, but also due to this very high contribution of the ion pairs. So that is possible in the liquid, but under very specific conditions. The other situation is a very extremely concentrated electrolyte, which is a water in salt electrolyte with a lithium TFSI, so kind of a very model system. And I don't know if you have been following that field, but there have been speculations that there is very fast lithium conduction and very high transference numbers. And if you look at the PFG NMR data, they do suggest that lithium moves quicker than the anion. So we took upon to look into the electrochemistry of these materials and try to actually measure the transference number. These materials are highly reactive. So just to tell you that it's not easy to measure transference number electrochemically, and we use the trick to use lithium iron phosphate in its half-discharge form as electrode. So for the first time to show that you do not have to use actually lithium metal to measure lithium transference numbers. But then we could actually measure that these lithium transference numbers are very, very low. So electrochemically, this is not a really great lithium transport material. So how can we explain that? And I think Monica already gave a little bit of insight of how that can happen, actually. So if we think about a material that contains ion pairs and ion triples, for example, then we can see that from this sigma polarization, which is the conductivity in the polarized state, there is a possibility to have a situation where actually lithium is transported predominantly by negatively charged species. So it's a very similar type of behavior that Monica already showed for ionic liquids. So in a way, we are very barely moving lithium, in this case, in the right direction. So in a way, although we have very high ionic conductivity, the ionic conductivity is predominantly anion-based. So I do not believe that these kind of materials will ever end up being in batteries of the future, but are, of course, very interesting to look at from the physical chemistry perspective. If we think about polymer-based hybrid electrolytes, we have to think about the complexity of ion movement in these kind of materials. So polymers might be either dry, where we have the movement of lithium ion on the chain, or they can contain a little bit of solvent, where we have this vehicular type of mechanism of movement. And once we start to add particles to it, first we amorphisize the polymer around those particles, but we might have also acid-base activity on the surface of the particles, where in the best of cases, we actually absorb the anion and immobilize it on the surface of those particles. So if you think about the ion transport mechanism, it becomes a kind of a tedious thing where we have maybe a vehicular mechanism, then also transport on the chain. If the particles are ionically conductive, then also transport through the particle, and finally also on the space charge zone. So it's a very complex thing. So how do we deal with that from the ion transport perspective? So I would suggest that we can use two different ways. One is the 2D random resistor model, for which we have to know the conductivity of the space charge zone, obviously, and the volume percent of the particles in the kind of resistor model. The other way that we have been using for many, many years is the parallel switching model, where we actually look at these pathways in parallel. And that means that we look at the conductivity of the polymer, of the bulk of the particles, and then finally of the space charge zones. And these A, B, and C parameters tells us how much of these pathways are percolating. So it's not always easy to access those parameters, but in one of the systems that is kind of the simplified version of it, which is the liquid-solid electrolytes, in which we have space charge zone formation at the interface. This can be sometimes possible. So in these electrolytes, we have an interfacial effect, but in order to have long-range transport, we need overlapping space charge zones. And then we can kind of describe this in this parallel switching model in terms of either ionic conductivity or the lithium transference number. And the interesting point here is that these effects, the interfacial effects, are strong in electrolytes with low dielectric constant, but we might have, of course, from the colloidal perspective, a massive problem in terms of colloidal network formation. So this is the reason why we try to invert the situation and make a material that is actually porous and infiltrated with a liquid electrolyte. So I'm showing you two of these examples. So one is a hierarchically porous silica that is infiltrated also with a glime type of electrolyte. And here the surface area is very high, the porosity is also very high, thus the surface effect is very high, and then we end up with transference numbers that are very, very high. In terms of another material, which is anodic alumina, where we have a relatively low surface area, we can achieve high transference numbers at very low salt concentrations, because then we still have the chance to absorb all of the anions. What I wanted to stress here is that rather than using a Bruce Vincent method to calculate or measure a transference number, where one has often these initial current issues, we use a galvanostatic polarization method, where we can really both geometrically but also calculate that initial potential. So I would kind of suggest that if you have ever problems with Bruce Evans' method, please try to invert the situation and just use the galvanostatic polarization method. And then very recently, an interesting case of what happens in a potassium-like electrolyte in this sense of liquid-solid electrolytes. If we use anodic alumina, and in this case, actually kind of a standard battery electrolyte, which is an EC-DMC with high dielectric constant, we see really, really high transference number with an order of magnitude lower diffusion coefficient, which means in a way that the absorption is stronger, but the movement of potassium is sluggish. And then the interesting point is also that we could actually measure this transference number, even though we are talking about potassium that does show on the longer run the instability in terms of SEI growth. But initially, it's quite stable SEI, and it's possible to measure the transference number. So far I talked about bulk properties, but what about the interfaces? So we've heard a lot about dendrite growth and all sorts of problems that metal anodes actually show. So what I would like to stress is what are actually the ways of dealing with that? How can we deal with the continuous SEI growth because lithium or any other alkali metal is not thermodynamically stable with other phases? And how do we deal with dendrite growth? Well, people have tried so far to employ artificial SEIs as a kind of a cure for continuous SEI growth situation, but also we know that there is a really big body of work on additives, which are kind of secret sauce to make batteries work. On the other hand, for dendrite growth, we know that we might try to use materials that have high cationic transference number. This is one of the options if we look at the crossover current values. The other ways is actually applying external pressure and trying to kind of press those dendrites away. And then I would like to stress that we have additional problems, and these are all of these dead electrode mass, volume expansion, rough surfaces, and void formation. These are not actually solvable. And I think this is the reason why people are trying to go towards these anode-less materials, because in those, these kind of problems occur at the later stage in the kinetics of the materials. But in my opinion, if we think about anode-less, the continuous SEI growth will always be a problem, because we are actually depositing always a fresh lithium or fresh sodium and fresh potassium, and these are really, really reactive materials. So what I was thinking about in the last years quite a lot is about how actually the SEI grows on metal anodes. And in that sense, I can imagine two different mechanisms. And one is that we start with an alkali or alkaline earth metal, and then we form a certain initial film that is either electronically conductive or contains reactive radicals. And then this film actually grows from the solid-solid interface above. The other way that we can imagine the growth is that the initial film that is formed is porous. And that means that when we have this porous film in contact with the liquid electrolyte, either the solvent or the anion can actually diffuse through its pores and then again react at the liquid-solid interface. Of course, SEI is here shown as one material, but it's a very complex material containing out of many, many different phases. So it's very hard to deal with. So what we have been doing is actually trying to measure the evolution of this SEI in time. And the very nice way to do that is actually impedance spectroscopy in symmetric cells, where if you can see from this medium frequency semicircle, we can actually extract both the resistance of the SEI change in time, but we can also extract the activation energy of this process and see how this SEI evolves in time. And then, of course, we have to understand what happens chemically and morphologically in order to make any kind of conclusions. That means we have to do quite a lot of FIB-SEM, XPS, and TOF sims, and these are not easy techniques to apply to alkali metals, as we all know. So here are examples of what we have found in terms of lithium, sodium, and magnesium in some of the specific materials. So if we look at the lithium in the glyme case, we actually could see a change in the growth mechanism. This is, I'm talking about only open circuit voltage conditions. This is really important. That means no current has been applied in these systems. We see a change from surface growth to the diffusion type of growth. That is something that we know from the SEI growth studies on carbon. And then in case of sodium, we see that actually a very porous SEI grows at the very beginning, and it gets kind of filled in. The pores get filled in with time. And in magnesium case, we see quite a lot of mechanical instabilities in a long-term growth. So for me, the most important part was how to actually model the impedance data, because this is something that we collect quite a lot. And then I can suggest kind of two general ways of approaching these impedance data that we collect, either by taking into account the full complex porosity of these SEIs and trying to kind of model the diffusion. In that case, for example, for magnesium, we can see that we need a very tiny amount of liquid in order to have a dominant liquid pathways in the SEI in terms of transport. Or we can try to model one pore or channel with these kind of equivalent circuits and then say that we have many of these channels in parallel. And in the sodium case, both in the with lime and carbonate electrolytes, we see that we have this situation where we have highly porous dominant liquid pathways that then become something in between liquid and solid in time. If we build these kind of equivalent circuits, what's really important to see from it is that and that is what has been confusing for the impedance community for a really long time, is that the capacitance that we get from those semicircles in the medium frequency range are actually related to the bulk, so to the solid state part of the SEI, while the resistances are related to the channel. And this is why it was kind of confusing, the capacitances that we were getting from this one single semicircle since mid-90s. And then the question of this sodium lime case was puzzling us for many, many years. We've seen this strange behavior with very low resistance of the SEI for quite a long time, and then these kind of strange jumps. And this was an electrochemist's nightmare in terms of course, seeing this and reproducing this many, many times and trying to understand what is this actually corresponding to, and that this is not an artifact of our measurement. But we are quite confident that this is really the real behavior of this sodium lime system. So actually, many speculated that this is a very stable SEI at the beginning, and we dare to say that this is actually a very porous SEI with ion transport at the beginning, and then finally with very many mechanical instabilities afterwards. And we can, again, by using the parallel switching model actually this kind of system where we take into account the resistances of the solid in the initial state and the resistances on the solid in parallel and in perpendicular to our liquid. And then, of course, if we take these geometrical parameter and the volume fraction of the solid that is filling in the SEI as time-dependent parameters, then it's easy to actually parameterize this kind of growth. And then I wanted just to stress that the potassium is a kind of a really exciting alkali metal because it's so much more complex than lithium and sodium. It, first of all, has a much larger zoo of materials possible in the SEI, but also the native film is slightly more complex because we have a peroxide also forming. And there have been speculations that the fact that people do not get zero OCV voltage is related to SEI. I dare to say that it is not. It's always the end phases that define the OCV. But what is kind of positive is that the crossover current might be higher than in the case of lithium and sodium because we might have a kind of a surface smoothing since the diffusion coefficient of potassium on the surface of metal is much higher than in the lithium and sodium case. And then what is interesting is to understand these mechanical properties of this SEI in time and in terms of solid state transport. I'll try to kind of distinguish between the SEI and charge transfer resistance in this case. And how we started looking at these materials is actually by looking at the SEI growth under constant current conditions. And there we've seen something quite incredible happen. We've seen the resistance of the SEI dropping in time while the SEI was growing. And we could not actually distinguish this from the chemistry of it. So some years ago, we started looking into this and then decided to go 10 steps back and try to understand the OCV behavior before trying to understand the galvanostatic behavior. So there is quite many things to be done in this sense. And then I said that it's maybe sometimes very useful to try to make artificial SEIs. We tried that too, both with atomic layer deposition of aluminum oxide, but also with this kind of gas-solid reactions where we make sulfides on the surface. But unfortunately, both lithium and sodium sulfides were not actually passivating. So we see the impedance growth at this interface, both in liquid and solid state cells. And we believe that this is related with Pilling-Bedford ratio. So in principle, the Pilling-Bedford ratios tell us that no material can be dense on top of lithium and sodium. So we will always get some porosity, and it's always a kinetic question: when will this liquid or solid penetrate through them? I hope you enjoyed my take on some transport mechanisms through this multi-technique approach. I showed some ways of increasing cationic transference number is mildly related to fast charging. And then at the end, I showed quite a lot about the SCI growth on alkali and alkaline earth metals.